Assalamualaikum and hi. My name is Muhammad Nabi Shazwan bin Mashwadi and I am pleased to present my comparative analysis of SRAM and DRAM for the course IMJ32204 Computer Architecture. So this presentation title was SRAM vs DRAM Architecture and Application serves to fulfill the requirement for question 1 of the media-based assignment. Media-based assignment. To put this perspective, we are looking at two fundamental pillars of modern memory hierarchy. My objective today is to move beyond basic definition and provide a senior technical analysis of how these technologies differ in construction and performance. We will begin with the shared characteristic of RAM, which is random access memory, perform a deep dive into underlying silicon architecture of both static and dynamic RAM, which is SRAM and DRAM. And lastly, conclude with rigorous technical justification for their specific role in modern computing environment. So let's move to the second slide. Before we distinguish between type, which are SRAM and DRAM, we must understand the fundamental properties of a random access memory, which is RAM. In technical, RAM is a semiconductor-based volatile storage medium, which when the power suddenly cut off, then the data is gone. The defining feature, random access, refers to the ability of CPU to access any memory address directly. Unlike sequential storage, RAM provide constant time complexity, meaning the access latency is identical regardless of the physical location of the data on the chip. The technical implication of this the RAM serve as high-speed workspace for the CPU. Is it fundamentally volatile? It relies on volatile state maintenance. Without continuous power supply, the electrical charge latching state that represent our data are lost, which is totally lost once the power cut off. As a success coach would emphasize, understanding this volatility is the key to understanding why we need hierarchies of memory. From the fast, expensive register to the massive and slower main memory. Let's move to third slide, which is about SRAM, static random access memory. SRAM, we see a sophisticated circuit topology. SRAM store each bit of data in flip-flop, which typically require a 6 transistor or 60 configuration. To put this in perspective, these transistors are arranged in cross-couplet in inverter that create a bistable state. The term static in SRAM is critical here. As long as the power is supplied, which means static, the CMOS transistor maintain the logic state, one either 1 or 0, and indefinitely through a continuous feedback loop, which is keep supplying the power to make sure SRAM is working. The primary technical advantage is the lack of refresh requirement because the data is latched rather than stored as a charge. SRAM can be accessed almost instantly. This eliminates the cycle time overhead found in other memory type. However, this complexity is double-edged sword. Using 6 transistors for a single bit significantly reduce the latitudinal density of the chip, making it physically larger and much more expensive to produce than it is dynamic counterpart. So let's move to dynamic random access memory, which is DRAM. So if we compare SRAM and DRAM, in contrast, dynamic RAM or DRAM use vastly simpler. Um, Before this, I said that SRAM use 6 transistor configuration, but dynamic random access memory is much more simpler. It uses 1T1C, which is one transistor and one capacity architecture. This simplicity allows for incredible areal density, which is why we can have 16 uh, or up to 32 gigabyte of DRAM in a standard laptop, while only having a few megabyte of SRAM. However, the dynamic nature of DRAM introduced a significant engineering challenge, such as capacity leakage. Capacitor naturally lost their electrical charge over time. To prevent data corruption in DRAM, the memory controller must perform refresh operation, essentially reading the data and writing it back to restore the full voltage level. The technical implication is that DRAM is subject to higher access latency. Every time a refresh cycle occurs, the memory is temporarily unavailable to the CPU. This creates a cycle time overheat that makes DRAM inherently slower than SRAM, despite its massive capacity and cost advantage. So let's move to fifth slide, which is comparison of SRAM and DRAM. So this table provides a high-level synthesis of our comparison, while SRAM wins on a pure performance and reliability. It lost on scale and cost. Obviously, DRAM provides the massive capacity required for modern operating system, but introduce latency through its refresh requirement. So, SRAM use bistable latching, whereas DRAM relies on voltage level in capacitor. This fundamentally different in how they store data. What we call the variation in state, is what dictate their divergent role in a computer architecture. As we transition to our justification, keep in mind that modern computer is not a choice between these two. Modern computer use both SRAM and DRAM to balance speed against capacity. SRAM is speed, DRAM is capacity. So let's move to the sixth slide. To achieve the excellent threshold in our analysis, we must justify this selection through four specific metrics. First, storage capacity. We choose DRAM for main memory because of high error density. A 1T1C, one transistor and one capacitor cell is significantly smaller than a 6 transistor SRAM cell, allowing us to fit billions of bits on a single silicon die. I mean, on a single silicon. SRAM construction is simply too bulky for large scale storage. Second, is that the first one was storage capacity. And the second is construction. The circuit topology of SRAM, which is the flip-flop, is designed for speed and state retention without external help. DRAM is built for simplicity. It's too bulky but it's simple. That is power consumption. This is nuance trade-off. SRAM consumes significant static power, which is the supply, because even when idle, many transistors suffer from leakage current. DRAM, however, require refresh power to constantly top up the capacitor. In large memory, DRAM DRAM is generally more power efficient per gigabyte, while SRAM is optimized for active power of high speed switching in the cage. Finally, speed between SRAM and DRAM. Uh, cache memory must, finally speed. Cache memory must match the gigahertz speed of CPU. SRAM is the only choice here because it eliminates the refresh and pre-charge latency inherent in DRAM. As I mentioned at the start that SRAM is prioritized in speed, DRAM is prioritized in capacity. See? So when the CPU need a bit of data from cache, SRAM provide almost instantly because SRAM is specialty in speed, where DRAM would introduce unacceptable wait state because it's slow. So for last slide is conclusion. So in conclusion, the choice between SRAM and DRAM is not about which is better, but which is appropriate, but which is appropriate for a specific tier of the memory hierarchy. SRAM provide extreme velocity required for CPU cache, ensuring our processor are not choked by waiting for data. So then DRAM provide a massive cost-effective scale. It provide a massive then cost-effective scale, it much more cheaper than SRAM for memory, allowing us to run complex and data-heavy application. Just remember that uh, SRAM is specialized in speed to provide the data almost instantly, and DRAM specialized in specialized for memory lah, allow us to because it big. I mean, it specialized in capacity. Then together combination of SRAM and DRAM, they create a balanced computer architecture. SRAM for performance and DRAM for skill. SRAM for speed and DRAM for capacity. I hope this technical deep dive has clarified why these technologies remain the standard in our field. Thank you for your time and for listening for my presentation. Uh, Thank you. That's all. Bye bye.